Hi guys, thanks for watching again. In this video we will be focusing on how to use a shift register. A shift register is a way to save pins on our board while still controlling up to, in this case, 8 LEDs by only 3 inputs. So what do we need for this little part of our project? We need a Arduino Leonardo with a breadboard, of course. We need a 595 shift register. In the description I will put a link to which one I've got, just to make sure you get the right one. And besides that we need 8 LEDs with 8 470R resistors, and we need some cables to wire everything up. Now, if we take a closer look at our shift register, we see that it has 16 pins, 8 pins on one side and 8 pins on the other. Another handy thing to look out for is the little gap in the plastic on one of the sides, and this is going to help us to determine which side is which, and it's going to determine where the pins are going. Well, as you can see, it has 8 pins on one side and 8 pins on the other. Well, on our little shift register, that means that we can control up to 8 LEDs by using only 8 outputs on the register, while it only takes 3 inputs from the board. So if we want to insert it on the breadboard, I'm going to place it on the little gap in the middle. Make sure that it's in there. Don't force anything if it's too stubborn. Perhaps something's in the way. Just be careful that you don't break the pins. Okay, the first thing we always do is just wire up the basics. And in our case, that's going to be the ground wire that's going to the blue horizontal line, and our 5 volts that's going to our red horizontal line on the first horizontal rows. As you can see, the entire line is powered now. I'm going to move them down a bit just to have some room to hook up the other sides in a few minutes or seconds. I'm not that slow, unless I pick the wrong hole. Then it's going to take some while. So as you can see, 5 volts going to the red line and ground going to the blue line. Now one thing we're going to do is we're going to connect the ground from the right side or to the left side by just hooking it up with a simple cable. So now both sides are wired up to the ground. Now, as you can see with the shift register, the side with the indent in the plastic is up, and in our pins need to have power on the third from the bottom and the first from the top, and the ground on the left, the farthest down. I will show you a diagram of these pins just so it gets clearer for you. So if we take a look at our pin diagrams, we can see the same 16 pins as we saw on our physical device. And the green ones highlighted are the outputs, 0 till 7. The red ones are power in. And we have the grounds on the brown ochreish color as represented in this diagram. Our data will be coming in through series. That means it will come in through a single line of information that will enter through the 14th pin. From there on out, it will get distributed to the corresponding outputs. And once everything is ready to be sent out, it will send out all the data at once over our 7 outputs. And I hope this will give you a bit of a clearer idea how a shift register itself. So as we've just seen, we're going to wire up the shift register accordingly. So we're going to start with our power on the top row. And we need a second power on the, it says second from last on the bottom row. Here we go. Quick closer look. And of course it will get power from the horizontal power line we've just connected to our board. So that's taken care of. Well, if we tackle the simplest part first, we're going to hook up the ground, which is going to be on the first pin of the left side, on the bottom, counted from the bottom. And if you leave a gap of 2 rows, you can place a ground on the right side. So 2 rows on top with the power and 2 rows from the bottom power. Or just as you would like to have it a bit easier, it's the 4th pin on our shift register. So now we've got a ground wired up, and as you noticed, we've bridged the gap before on top, so both sides have a path back to our board. Now, as I've mentioned, the data pin, and this is the pin that will be going to our 8th pin in our example. We still need to hook up 2 more pins, which I'm going to explain later on when we're coding, but it's going to be on the remaining holes left on the right side, if you don't count the bottom one. And we're going to plug them in on 12 and 13 on our board. So in this example, I've made a little gap just to have a clearer visual representation, because the data pin is going to be handling our data, and the other 2 are more of a technical wire, which I will explain at the coding part later on, so you don't have to worry about that for now. The rest of the wiring is actually pretty simple. We just take a cable and hook up every remaining pin up to a resistor, which runs through our LED and back to a ground line. In this case, on the other board, you could use the same board. This was just a bit clearer to show in a video, so that's why I've chosen this one. So as you can see, every pin will get their own cable, and the first one on the right side will actually be left open. So the only thing that's left is to just hook up our second board, or if you have it on the same board, it's probably already hooked up to ground. Don't forget to bridge the gaps with the resistors and the LEDs. And then the final step will be to just connect both. And in my case, I've already uploaded my code, so I can just turn on the power on my board and the LEDs will light up. In your case, nothing will happen yet, or maybe it does, but that's no problem. We will go over that in a second, and then you will have a clue of what is happening and why it's happening. I see that my red LED is broken, but that's no problem. So I see you in the coding part. Thanks. I've briefly explained that we had a data pin, which in our case is in pin 8, I believe. Yeah, sorry. We have a latch pin. This is going to act like a gate. It's a pin 12. And we have a clock pin, which is in gate 13. I'm going to explain what they do in a second. Data pin is the pin where we send the data from. Latch pin, you could see it as a gate saying, okay, data is coming in. Data is all in, let's close it. I have a clock pin that just determines the frequency at which data gets passed towards the data pin. So we start by defining what these are. So we're going to say pin mode, data pin, comma is an output, all capitals. And we're going to say pin mode, data pin, latch pin, also an output. And we're going to say pin mode, clock pin, and last but not least, but also an output. So in all outputs, nothing out of the ordinary. And just so we can debug later on, we're going to start by defining a serial connection at 6900. We're going to be using that later on to see what the actual real value is we're passing through the data pin. Okay, so we have 8 LEDs and 8 outputs and only 3 pins. So our data pin on pin 8 is going to accept bytes. 8-bit bytes. So that means 8 bits is 8 times 0, 1, 2, 3, 4, 5, 6, 7, 8, or ones, or a mix of both, whatever is needed. In our case, each bit of our 8-bit byte will represent a light. So the first one is our first light, second light, third light, fourth light, etc. If it's 0, it's off. If it's a 1, it's going to be on. So in our case, if we would want the first and the last one to be lit, we would send this. And if we would want to invert it, we could do this. So 1 is on and 0 is off. Now, each of these ones or zeros represent a value. So 1, 2, 3, 1, 2, 4. So you just multiply by 2. 8, 16, multiply by 2, 32, 64, and 128. So our first light, if it's on, it has a value of 1. If a second light is on, it has a value of 2. If the first and second one are on, it has a value of 3. It's 1 and 1 is 1 plus 2 is 3. If you want to do 5, it's going to be the third light and the first light. It's going to be 12, it's going to be the fourth and third light, etc. So you just got to remember 8 and just keep multiplying by 2. So the first thing we're going to do is create a function that can actually change our lights depending on the value we pass it. So in this case, I called it update shift register, and it requires a value to update. So as I already mentioned, the latch pin is acting like a kind of gatekeeper. So if it's low, data is flowing in. If it's high, we're done. So we're going to digital write to the latch pin a low state. So data is going to start entering and it's going to be listening. And Arduino has a function built in that's called shift out. And we're going to shift towards the data pin with the clock pin located at pin 13. I'm going to do MSB first, which is all in capitals. And this is going to determine if we start on one side or the other. We could use the other one as well, but this is just for this example sake. And after we've shifted our value, we're going to say, okay, latch pin, we're done. So latch pin is going to be high again. So in theory, we could already test this by saying, okay, I want to update my shift register. And as we mentioned, these are the values represented by this. So let's say I want to do 64. And let's see what happens. As you can see, the second to last light is turned on. If we change this to 128, the last light will turn on. If we change it to 1, the first one will change, etc. So you want to avoid to always have to do the math to see which light is which value. So we're going to store it into an array. So we're going to say, okay, int byte values. It's going to hold 8 values. So we're going to say byte values is going to be ints. It's going to be 8 of them. And here we're going to define what these values are. So it's going to be multiplied by 2. It's going to be 2, 3, 4, 8, 16, 32, 64, and 128. So keep multiplying by 2. So if we would say, okay, I want to update this, we could say by its values on which one we want the first one. So you want to update with 1. I'm going to say 0. You might wonder why 0? An array in most programming languages always starts at 0. So this is entry 0, 1, 2, 3, 4, 5, 6, 7, 8. But, 0, 1, 2, 3, 4, 5, 6, 8. Do I have one too many? 1, 2, oh, the 3 doesn't belong here. That explains a lot. So once again, 0, 1, 2, 3, 4, 5, 6, 7. So don't go around saying I want the 8th value, because there is no. So we're going to be saying 0 and I'm going to upload it. And in theory, nothing should be happening because the light is already on. Maybe it will flicker for a second. Oh yeah, it will turn off first. But it will do exactly the same because it will call this value and pass it along. Now next we need to know which light is on or off to determine which value needs to be passed to the buttons. Because what we've been doing in our end product, which we will be seeing later on. Oh, I accidentally bumped something, but if I press this button, it will remember the state and it will see which lights to turn on. So let me quickly replug it. So we're going to say, we're going to make another array, but it's going to be of the type Boolean. Button states, we're going to call it, and also going to contain 8 values. And Booleans are nothing more than values that are either false or true. In this case, we're going to say everything is off from the beginning. So false, false, false. I'm going to do that 8 times. So that's 1, 2, 3, 4, 5, 6, 7, 8. And once again, the first false is 0 and the last one is 7 because it's an array filled with Booleans. So true or false. Now we've created a function to update the register. And we're going to do the same for the button states. So let's say update button states, quite concise in our naming. And we're going to pass it a value. So what's going to happen? Right now everything is false. So we need to check if it's off. We don't need to turn it off. We need to turn it on. And if it's on, we need to turn it off. So I'm going to see if button states value. So if we're going to call this function, we're going to say I want to see if button 0, so the first one, is true or false. So if button states 0 is true, we're going to do something. And what are we going to do? We're going to change the button states value to false. If it's the other way around, so if it isn't false, it's true, vice versa. So now we just say, okay, then we just do the same, but we will make it true. What we've actually created is a little toggle that says, if this gets called and it's on, turn it off. If this gets called and it's off, turn it on. As we can see, we had our values and we had the states. So if this is on, that would mean that this value is active. We're going to create a counter. We're just going to call value. It's going to be 0 to start with. every time it's turned off, we're going to say value is the value minus the byte values at the same position as the button state. So if we're checking button state 0, we also want to have the value that corresponds to that. So we do the value minus button values val, and if it's the other way around, we're going to be doing value is value minus plus byte values val. So if it's on, off, subtract the value. If it needs to be turned on, we're going to add the value. So if these two are true, we're going to have a value over here of 3. If these 3 are true, it's going to be 7, and you can do the math for the rest. So let's say in our case, in our loop function, we want our light state. Oh, I call it update. Update button states. Update button states. And we want to turn the first one on because everything is off right now. We want to turn the, let's say, the 5th one on. And we want to turn the last one on, which is going to be 7. So once again, 7 is the last one, 0 is the first one. And then we're going to be updating the shift register right here. We're going to pass it our counter value. So this one. Remove this. We don't need this anymore. As you might see, I'm going to put in a little delay because it's going to flicker. And I'm going to explain why. Delay of 500. Now we upload it. Oops, forgot to close this one. And as we told it, the first one, the 5th one, and the last one, or the 6th one and the 8th one, as you might see it. And why it's flickering is actually because what we desired to do is working. Because we said, okay, if it's false, so this block, if it's false, make it true. If it's true, make it false. And the loop will keep on repeating every 500 milliseconds. So every time it will just change from true to false and alter the states accordingly. So this is working as expected. And we could also, if we would do update button states twice, so update button state 7, we might notice that the last one will never turn on, because we will say, okay, it's false, make it true. And then we say once again, okay, it's true. Then we make it false again, and then we update the value. So that's why the last one is never turning on again. And right now, this might seem a bit, why do we need this? Well, first of all, we would never be able to control 8 LEDs via the board if we wanted to achieve something with our radio control unit. So that's why we need this technique. And this technique will actually be used with the arrays that we've used to store the state of the buttons we press on the controller and to change the lights below accordingly. I just wanted to close off by saying thanks for the support. In the next few videos, we will be wrapping up this entire project by hooking everything up to the same board and actually get a product that we can use in game to change the radio frequency, altimeter, whatever you'd like. So keep an eye out for that. Leave a comment down below if you have any questions, and I'll see you in the next one. Thanks.